I want to give you my, let's say, nutshell definition of what mathematics is, what we do as mathematicians, as students of math. So if I was going to say it in one sentence or one equation, how about that? So math equals, well, let's see now, what do we do? Well, if you think about all the classes that you've taken, all your advanced classes, sets are involved, right? We study sets that have some sort of structure on them. For example, when you study groups, well, what's a group? It's a set that has some axioms. That's the additional structure that goes along with the set, right? What else? If you study linear algebra, you study vector spaces. What is that? Well, it's a set together with some axioms that describe what, or define what a vector space is. So math is the study of sets with structure, but not just the sets, right? There's always some functions that go along with there. And so those are, so I'll say plus structure preserving functions, which we often refer to in sort of a more abstract, generic sense as maps. Right? So, for example, who are the structure preserving functions when you're studying groups? Those are the homomorphisms. What are the structure preserving functions when you study vector spaces? Those are linear transformations and so on, right? And you've got continuity when you're studying real analysis. So math, this is my definition, study of sets with structure together with the structure preserving functions. Now, yeah, so this is an important part, right? You don't just study the groups, you study the homomorphisms, you study the linear transformations, you study the continuous or the differentiable functions. And so in the study of these functions, here's a general question. The general question, let me say, so extending maps is an important question or facet of the study of these functions. Now, I need to say what I mean by extending maps. So let me just say it here first in the set theoretic sense. So, so here's what we mean by extending. So if f is a function, let's say from A to C, and A is a subset of B. Right, so here I'll just draw a little picture here. So I've got a function, f, from A to C, but then A is sitting inside some bigger set B. And so the question is, the idea or the question related to this notion of extending maps is, can you, given the function from A to B, can you extend the function to a larger domain? And so that would go like this. So if f is a function from A to C and A is a subset of B, does there exist a function g from B to C such that g restricted to A is equal to f? Right, so you extend now to a function g with the provision that if you plug something from A into G, it has to do exactly what f does to that same element. Right, so that's that's the idea behind extending maps. Now here I stated this in terms of functions, but then you could add that not only is it a function, but it's a map in the appropriate category, meaning that it's a homomorphism or a linear transformation or a continuous function and so on, right? And so then, right, does there exist a map G that extends F? Right, so there's the general question. And I guess this should have a question mark at the end. And here's a famous example. Let me just say, so in this case, we say F has been extended to G, and this is sort of unfortunate, so we could say, or G is an extension of f. And so we have to be careful now when we use the word extension, right, when we're studying fields, of course, because we'll need to understand from context, do we mean an extension of a function, a homomorphism in this case, or do we mean an extension in the field setting, right? So one field extending the other. So here's one famous example. So yeah. So the famous example, it's called the Tizzi extension theorem. Now, I'm going to use some words. If you haven't taken topology, there's a couple of words that you might not recognize, but once you've taken topology, you'll remember back and think about this. So it goes like this. If x is a normal, or let's just say if x is normal, and A in x is closed, and we have a function and f from A to R is continuous, then it turns out that there's always an extension of f to the entire set x, right, that is still continuous. So then there exists a continuous extension g, or let's just say continuous function. So continuous g from x to r, such that g restricted to A is equal to f. All right, so there's one example. If you have a normal space and a closed subset, any function from your closed subset to R can be extended to a function to all of x. Here's another example that we're actually going to make use of today. Right, so this is now going to be in the field context. So so first, well, let's say let I from K to L be so we just need a homomorphism here. So be a homomorphisms. All right, so we just have a homomorphism from one field to another. Now, here's an interesting fact or observation. So let's say note that if there's some non-zero element in the kernel, so let's call it a little alpha. So if alpha not equal to 0 is in the kernel of I, then, all right, what would that tell us? So then K equals the ideal generated by alpha. Oh, wait, why? Well, K is a field. Every non-zero element is a unit, and if you look at the ideal generated by any unit, it gives you the entire ring, right? And so, if we have a non-zero element, right, the ideal generated by that element has to equal the entire field. But alpha lives inside the kernel of I. The kernel is always an ideal, and so the ideal generated by alpha has to be contained in the kernel of I. Oh, so what does that mean then? Well, if the entire domain is contained in the kernel, that means that every element gets sent to 0. And so what that means is that I is the trivial homomorphism. So we can say, and so I is the zero homomorphism or the trivial homomorphism. So obviously this does not happen in the group theoretic setting or in the ring theoretic setting, but in the field setting, if you have a homomorphism and it has any non-zero element, if it has non-trivial kernel, then it has to be the zero homomorphism. Otherwise, it has to have trivial kernel, which means that it is then one-to-one. So otherwise, I is a mono. So that's sort of strange behavior, or at least surprising behavior, right? It's not like when you study groups or rings where you can have lots of different kinds of mappings. In this case, if you've got a homomorphism, it's either the zero homomorphism or it's a monomorphism. So now we can view, I'm still working in this within this example here, so we can view K as being a subset of K bracket X. You can think of K as the constant polynomials within K bracket X. And so we have, all right, still working with this homomorphism. I want to assume that we have non-trivial, or that we have trivial kernel here, so that we've got a monomorphism. And so now what we have is an extension. So we have an extension, and I'm not going to change the name of it, right? So I've got this monomorphism, right? We're assuming we're in the otherwise category right here, so that we have no non-zero elements in the kernel. And so if we have this monomorphism right here, it easily extends. So we have an extension. And I don't want to change the name. I don't want to change the symbol that I use. So I'm going to call it I as well. But anyway, so I get this extension like this. And how does it work? It goes from K bracket X to L bracket X. And how does it work? Well, you've got a polynomial whose coefficients are in K. Just apply I to each of the coefficients. So it's given by I of A0 plus A1x plus dot 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 plus A n x to the n equal to I of A0 plus I of A1x plus dot 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 plus I of a n x to the n. And this, it's easy to check, is also a monomorphism. So we can say which is also a monomorphism. So here's another example of an extension in the field or ring theory, the polynomial ring setting, right? By thinking, once you have this mapping from, all right, so we've got I from K to L, it induces a homomorphism from K bracket X to L bracket X. It will also be a monomorphism, right? And the definition is just, you just do the obvious thing here. All right, and so we're going to make use of this. All right, there's nothing exciting going on here. You might be a little disturbed by the fact that I'm not changing the name. It's a common thing. I mean, it's sometimes referred to as abusive notation. But there are times when you just don't want to create new notation, right? We've got this original mapping I from K to L. And by doing the obvious thing here, we get a new homomorphism from K bracket X to L bracket X. I'm going to call it I as well. All right, so now the theorem that we're about to state and prove here, it's not, it doesn't look obvious right away. It won't be obvious, but this theorem is, you could say it's why Galois theory works, right? So this theorem is definitely important. So it goes like this, right? But this is a biggie. So let's let alpha be algebraic over K. And I mean, when we say this, right, alpha has to live in some field that contains K. I don't care who it is. We know, right, when I say, I mean, if we have a function, or if we have an algebraic element, what that means is just as a root of a polynomial in K bracket X. So alpha just lives in some extension of K. I don't care who it is, right? So we'll say, yeah, I mean, you can apply Kroneker's theorem if you like, right? When you have a polynomial, it's got roots that live in some larger field. If you want, you can think of it as the one that you get from Kroneker. Doesn't matter. Okay, so we've got an algebraic element. And we have a monomorphism I from K to L, so let's let this be a monomorphism. And now notice from our previous observation, when we say monomorphism, that's not a big deal in this case, right? You're either the zero homomorphism or you're a monomorphism, right? There's no in between. So let's see, we've got a monomorphism, and one last thing, let's take beta in L. All right, so we have an algebraic element, a monomorphism, and an element of the codomain. So then, there exists an extension, and I'm going to call it J, from K adjoin alpha to L, such that J of alpha equals beta if and only if I of, let me say this correctly, yeah, I of the minimal polynomial applied to beta is equal to 0. Where this I is the mapping induced by this monomorphism. It's the mapping from K bracket X to L bracket X. So, oh, and there's a little bit more, there's a uniqueness here. So if J exists, then it's a unique, so let me finish off the statement here. So moreover, if J exists, then J is unique. Okay, so for the proof, we first look at the forward direction, so we are going to assume that we have an extension that takes alpha to beta. Okay, so let's write this out. So let's assume that J from K adjoin alpha to L is such that, so what do we know? It's an extension, so that means that J restricted to K is equal to I, and J of alpha equals beta. Okay, so now what I need to do, I need to take the minimal polynomial for alpha, plug it into I. That's going to give me a polynomial in L bracket x, and I need to plug beta into it. Right? So let's write it out. So let's write m sub alpha. So that's going to be a polynomial in k bracket x. So let's write it as, say, k0 plus k1 x plus dot 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 plus k sub n x to the n. So then, let's look at what happens. So I need to apply I of m sub alpha. Do I want to do it all in one shot? Yeah, I guess I'm just going to do it all in one piece here. Right, so I of m alpha is going to be the polynomial that you get by applying I to each of those coefficients, right? So that's equal to I of k0 plus I of k1 beta. I'm plugging beta into the resulting polynomial. I'm just going to, you can think of it as skipping a step. I just want to get it done. So plus I of k1 times beta plus dot 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 plus I of k sub n beta raised to the n. Okay, now let's see, what do we know? Well, we know that j restricted to k is equal to I. And so I of k0 is exactly the same as j of k0. Same thing with all of the other coefficients. So I can write this as j of k0 plus j of k1. And then, oh, by the way, beta is j of alpha. So I can write this as j of alpha plus dot 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 plus j of kn times j of beta the n. Now, of course, j is a homomorphism, so I can combine this all into one piece. So this is going to be j of k0 plus k1 alpha plus dot 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 plus kn alpha to the n. Oops. Freaking chalk. And then what is this? Well, this is the minimal polynomial for alpha with alpha plugged in. That's 0, right? So that's equal to j of 0, which equals 0. Okay, so that wasn't so hard. We're assuming that it exists, so I want to prove the uniqueness portion as well. So, right, and then we'll prove the reverse direction afterwards. So, if it exists, now we want to prove uniqueness. And so what we're going to say is, suppose that we have another extension of I that takes alpha to beta. Let's what do I call it here? H. So suppose H from K adjoint alpha to L is a monomorphism where H restricted to K is equal to I, and H of alpha equals beta. Now, okay, so what do I need to do? I need to show that H is equal to J, which means I need to show that if I take any element in K adjoint alpha and plug it into H and plug it into J, I get the same result. So let's think about what elements of K adjoint alpha are. Well, our minimal polynomial had degree n, and so we know that a basis for K adjoint alpha is going to be 1 alpha alpha squared all the way up to alpha raised to the n minus 1. Since, let's start here. So since 1 alpha up to alpha n minus 1 is a basis for a K adjoint alpha over K, if little z is in K adjoint alpha, then z is equal to K0 alpha plus K1, K0 plus K1 alpha plus dot 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 plus K n minus 1 alpha to the n minus 1 for some K sub I in capital K. Okay, so now I just want to look at H. I'm going to plug Z into H and see what we get. We want to compare that or hope that what we get is exactly the same if we had J, or if we use J. So now, H of Z is equal to H of this linear combination, so K0 plus K1 alpha plus blah, 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 plus Kn minus 1 alpha n minus 1. And we're gonna do this quite a bit now, so hopefully you'll get familiar with it. So I'm gonna start applying it individually to the elements, right? So this is H of K0 plus H of K1 H of alpha plus dot 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 plus H of K sub n minus 1 H of alpha to the n minus 1. All right, what's next? Well, two things. First of all, we know that H, excuse me, H applied to any element of K is the same as I applied to any element of K. Also, we know that H of alpha is equal to beta. So what we'll get is I of K0 plus I of K1 beta plus dot 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 plus I of Kn minus 1 times beta to the n minus 1. But then I matches J when we're restricted to capital K. And so this is equal to J of K0 plus J of K1. Oh, and then who's beta? Well, beta is J of alpha. So that's J of alpha plus dot 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 plus J Kn minus 1. J of alpha to the n minus 1. And now we just unravel this, right? So I'm just going to write it down. Do the same thing. This is equal to J of Z. All right, just using the fact that it's a homomorphism, you can unravel this one more step, which I'm going to let you do. I'm not going to do it. Okay, so that takes care of the uniqueness, right? So we can say, therefore, H equals J. So the what can I say? The forward direction is easy. We didn't need any really high-powered anything, right? Just the fact that we've got a homomorphism is all we need. The reverse direction takes a little bit more technology, right? So this is gonna this is kind of tough actually, or at least I don't know if it's tough. It's fun. And I mean, if you're taking if you're taking this class as Math 560 and you plan to use this as part of your qualifying exam, this class as part of your qualifying exam, this is just a typical question. Prove this theorem, right? So it has a nice picture that goes along with it. It does have some steps, but none of the steps are particularly difficult. You just got to get all the steps in the right order. So, okay, so now we're going in the reverse direction, which means that we're going to assume that I applied to the minimal polynomial, or I of m sub alpha of beta is equal to 0, right? So assume that beta is a root of the minimal, or I of the minimal polynomial. Now, right, remember we have this monomorphism I from K to L. We know that I is 1 to 1, so let's write I, or let's use K prime. That's going to be I of K. Now, we know that I is a monomorphism, so since I is a monomorphism, if we think of, if we restrict the codomain, so since I is a monomorphism, I from K, if we don't go all the way to L, if we look at K prime, right, we know that it's 1 to 1 if we put an L here. If we shrink down to K prime, now it's also onto. And so this is an isomorphism. Now, okay, fine. We have an isomorphism from K to K prime. That will extend to an isomorphism from K bracket X to K prime bracket X. So this extends, and I'm going to use that same symbol I. So this extends to an isomorphism I from K bracket X to K prime bracket X. Just a reminder, so I'll just say recall, this was way back in theorem 1, well not that far back, but so recall from theorem 1.4, what we have is that K adjoint alpha is equal to the image of the evaluation map E sub alpha. All right, so that's just a reminder. Also, so I also want to note, so let's say also note that, so let's see what we have here. Beta is a root of this polynomial right here, and this polynomial lives in, so I of m of alpha lives in K prime bracket X, which means that beta is algebraic over K prime. So also note that since I of m alpha of beta equals 0, we have that beta is algebraic over K prime. All right. Now, I'm going to start drawing some diagrams here, and we're going to start sort of pasting diagrams together. So here's what we have first. Right, I've got K bracket X. If you apply the evaluation mapping, right, that's going to take us now, right, the image of the evaluation mapping is K adjoint alpha. So we have E sub alpha. We have the projection mapping that takes us to the quotient K bracket X mod the ideal generated by m sub alpha. And then we know by the first isomorphism theorem that this quotient is isomorphic to K adjoint alpha. All right, so this is an isomorphism. And I want to give, let's call this one E sub alpha tilde, right? So here, E, whoops. So here, E sub alpha tilde is the isomorphism that arises from the first isomorphism theorem Why is that? Well, M sub alpha, by definition, right, is the generator of the kernel of the evaluation mapping. Right? And so what do we have? We have, right, so this ideal is exactly the kernel of the evaluation mapping, and so we have domain mod kernel isomorphic to image. Right? That's just first isomorphism theorem. And just to remind you how this mapping goes, right? So let's see, E sub alpha tilde. What does that do? Well, it takes a coset, right? So this would be F plus ideal generated by M sub alpha, and it gives you F of alpha. Just plug alpha into the polynomial and drop the coset representative. Or drop the coset part. Okay, so there's sort of step one. The next step, now, so since I, from K bracket X to K prime bracket X, is an isomorphism, I of M sub alpha is irreducible over K prime. Now, why is that? Well, if we could factor I of M sub alpha, that would give us a factorization of M sub alpha, right? So let's say it like this. So here's the reason a factorization of I of M alpha would induce a factorization of M sub alpha itself, but we know that M sub alpha is irreducible over K. Right? How would you get that? Well, if you had a factorization here, just apply I inverse to the factorization. That would spit out a factorization of M sub alpha sitting in K bracket X. Okay, fine. Okay, so what does that tell us then? Well, M sub alpha is monic. If you apply I to 1, you get 1. And so I of M sub alpha is monic. It's irreducible, and beta is a root. In other words, I of M sub alpha is the minimal polynomial for beta in K prime. So we can say it like this. So it follows, or let me say a little bit more. So since, or let me write a little more. Since I of M sub alpha is monic, and I just keep writing this, but that's all right. M alpha of beta equals 0. We conclude that I of M sub alpha is equal to M sub beta, the minimal polynomial for beta. And you should note in context, right? M sub alpha is a polynomial with coefficients in K, so if you really wanted to get technical, right, it's M sub alpha K, and then M sub beta, right, this polynomial, right, lives in K prime, or has coefficients in K prime. Okay. So this gives us the diagram. So let me see what I have. I have K prime bracket X goes by evaluation at beta to K prime adjoin beta. There is a quotient, let's call it Q prime here, and that's going to go to K prime bracket X mod the ideal generated by M sub beta. And then once again, first isomorphism theorem gives us a homomorphism, which we will call E sub beta tilde. So once again, there's an isomorphism. So I have two of these triangular diagrams right here. And let's try to remember what we're looking for, right? Remember, we're looking for an extension of I. Right? I'm looking for a J. So let's sort of take a look at what we have so far. And what I want to do, I just want to focus on the diagonals of both of those diagrams, right? We've got a couple of isomorphisms here. So far, on the one hand, I've got K adjoin alpha, and then I've got E sub alpha tilde mapping from K bracket X mod ideal generated by M sub alpha. These diagrams really help you keep your head straight. I mean, field theory, I don't see a good geometric picture. There's really not a good geometric picture, at least as far as I'm concerned, when it comes to field theory. But these diagrams sort of help you keep your head straight, right? And so also what we have is we've got K prime bracket X mod ideal generated by M sub beta to K prime adjoin beta. Now K prime sits inside L, so does beta, so this is a subfield of L. And what were we looking for? We're looking for an extension of I. We need a mapping, and so we need a mapping from K adjoin alpha into L. Oh, let me call it, sorry, that's E beta tilde. So here's the idea. I wish I could bridge this gap. I mean, notice at least here, if I could, this is an isomorphism, so I can go in the reverse direction. If I could somehow piece things together, right, I would have a function at least. I mean, I can't claim right away that it's an extension, but at least we could come up with a function from there to here if we could figure out what to put there. All right, so far this is the stage. This is where we're at. And so my next goal is actually to come up with a function from here to here. So, and I want to be careful. I mean, you know, this is a domain that's got, the domain consists of cosets, equivalence classes, and so you got to be careful with well-definedness. I don't want to just out of the blue define a function from here to here, right? I'm going to let basically first isomorphism theorem do the job for me. So let's see. So yeah, let's do it like this. So let's define I hat from K bracket X to K prime bracket X mod the ideal generated by M sub beta. Okay, so now I got to tell you how to define this. So let's see what we should do. So this is going to be defined by I hat. of some polynomial is going to be equal to, so remember, I takes a polynomial from here to a polynomial from here. So it's going to be I of f plus the ideal generated by m sub beta. This is sort of the obvious thing to do. Now, since I is an isomorphism, wait, what? Oh, right. Sorry, I tripped out for a second there. So since I hat is an isomorphism, which means that it's isomorphism, which means that it's onto k bracket or k prime bracket x. Oh, that should not be an I hat. Since I is an isomorphism, I hat is surjective. Right? If it's on to the numerator, then it's on to the quotient as well. Or yeah, whatever. Also, let's think about the kernel of I hat now. So, the kernel of I hat. Who do I want it to be? Well, think about what I want. I want an isomorphism here. Or at least I want a mapping. I want first isomorphism theorem to give me something here. So the kernel of I hat. Okay, so let's just think about the definition here. So the kernel of I hat is going to be the set of all polynomials. So that I of that polynomial lives inside the ideal generated by m beta. Right? So it's equal to the set of all f in k bracket x, such that I of f is an element of the ideal generated by m sub beta. So, yeah, so let's think about how this could possibly happen. So, I of f is an element of the ideal generated by m sub beta. Okay, what does that mean? It needs to be a multiple of m sub beta. So this is if and only if. I know I don't usually do this, but I got to write if and only if a bunch of times, so I'm going to use double arrows. I of f is in here, so if and only if I of f is equal to g times m beta for some g in k prime bracket x. Right, okay, fine. If and only if I of f is equal to g times, now what do we know about m beta? Well, did I erase it? M beta is equal to I of m alpha. So this, I didn't need to. Okay, so I of m alpha. If and only if. So now I'm going to apply I to both sides, or sorry, I inverse to both sides of this equation, right? I is an isomorphism. So if and only if f is equal to I inverse of g times m sub alpha. If and only if, okay, so what does that mean then? Oh, so if f is a multiple of m sub alpha, that means it lives in the ideal generated by m sub alpha. So this is if and only if f is an element of the ideal generated by m sub alpha. In other words, the kernel of I hat is exactly equal to the ideal generated by m sub alpha. So we can say, therefore, the kernel of I hat is equal to the ideal generated by m sub alpha. All right, so now what do we have? We have an onto homomorphism. We've identified its kernel, and so then first isomorphism theorem gives us an isomorphism between the quotient and the image. So by the first isomorphism theorem, morphism theorem, there is an isomorphism, which I'm going to call, I think I call it I tilde. I tilde. From K bracket X mod the ideal generated by M sub alpha to K prime bracket X mod the ideal generated by M sub beta. And let's say how this is defined, right? It's defined by so that's going to be I tilde of F plus ideal generated by M sub alpha. And then what do we do? Well, we apply I to F plus the ideal generated by M sub beta. All right, so that bridged the gap in that diagram that we had. And so I want to put the diagram back up. Yeah, I think I can fit it here. So let me say here. So I'm gonna write the diagram right there, but let me start my sentence. So now we have, so at the left-hand side we've got K adjoint alpha. Then we have K bracket X mod ideal generated by M sub alpha. Then we have K prime bracket X mod the ideal generated by M sub beta. Then we have K prime adjoint beta, and then we need to always remember that that's living inside L. And now let's write down the names of our functions here. So this one is E sub alpha tilde. This one is I tilde. And this one is E sub beta tilde. So we have this diagram where each one of these is an isomorphism, right? So that's an isomorphism, that's an isomorphism, that's an isomorphism. Now, what are we looking for? Well, we need a monomorphism from K adjoint alpha to L. Well, we've got an isomorphism that carries us to here, right? Which means that it's 1 to 1, and so it'll be a monomorphism into L. So I'm going to define J from K adjoint alpha to L by J equals, so it's going to be E beta tilde of I tilde of, now I'm going to do the inverse there, so that'll be E sub alpha tilde inverse. All right, so it's just the composition of those functions where we're taking the inverse in that direction. Okay, so now there's two things we need to do, right? Two things that this function needs to do. It needs to be an extension of I that takes alpha to beta. So it remains to check that. So two things. First, which order do I want to do this in? Restriction first. So J restricted to k equals I, and the second thing I need to check is that j of alpha equals beta. And these are both fairly straightforward to check. We just need to keep our head straight. For part one, we need to keep our head straight. Oh, actually, this one's not as bad, is it? Well, we just need to know what the formulas. We need to remember what each of those functions do, right? So for the first one, if we take little k in capital K and plug it into j, so then j of little k is equal to, well, it's this composition, e beta tilde of I tilde of e alpha tilde inverse of little k. And so that's equal to e beta tilde of I tilde of, okay, so what does e alpha inverse of k equal? Well, it just equals k plus the ideal generated by the minimal polynomial, like that. Right, because we're going from here to here. So then I apply I tilde. So that's going to equal e beta tilde. So when I apply I tilde to this, what do I get? Well, I get I of k plus ideal generated by m sub beta. Right? Yeah, I of k. I of k plus ideal generated by m beta. Okay, then we do e beta tilde, and what's that going to do? It's going to give us, right, we just evaluate, and so this is going to be, well, essentially we evaluate and we drop that right there, and so that's just going to be, well, if you plug beta into a constant polynomial, you just get the constant, right? So that's just I, so let's write it out like this. This is I of k of beta, but of course, if you plug beta into a constant polynomial, you just get the constant, and so that's I. Okay. So what does that tell us then? It tells us that j restricted to capital K is exactly equal to I. Right. Okay, so now I need to plug alpha into j and see what happens. So for the second thing to verify, so also j of alpha is equal to, so this will be e beta tilde of I tilde of e beta tilde inverse, oh no, alpha there, alpha. That's going to give us e beta tilde of I tilde of x plus ideal generated by m alpha. Got to think about that one for a second, right? Because we're doing the inverse function, it's going to give us the function so that when you apply e beta tilde to it, e alpha tilde to it, you get alpha. Well, how, what do I need here? I need x. So now this is equal to e beta tilde of, let's see, so now what does I tilde do to x? Well, it does I of x, which is just x. So this will be x plus ideal generated by m sub beta. And then, I put a beta there, that should be an e. And now, if we apply e beta tilde, what does that do? It takes beta, plugs it into x, and drops the ideal, and so that's equal to just beta. Well, that's it. It's kind of a fun proof, right? You're gonna have to go back and go through and check all the details and look at what's happening. And let's see, how long did we? Yeah, oh, the hours was exactly an hour. So let's put a celebration box at the end there, and let's take a break. I had to come up to my office late tonight. I was doing stuff all day. It's actually Saturday at 9:15 now. So I'm ready to edit this video and go home. So I'll see you next time. All right, bye.